right? Remember how we define Brillouin zone using the Wigner-Say's ideas for splitting our zone. And each Brillouin zone are identical in size, right? Because the first Brillouin zone is the same as the second Brillouin zone, and so forth. But in theory, you ought to be able to just show the first Brillouin zone. So here I show every zone. I got extend to from k go from 0 to infinity. But maybe I can just restrict one zone and show you. So here's what I try to do. Let me show you this. Rather messy, but so you look at what I got just before. My parabola is like this. My parabola go from here to here. Right, this is my original extended zone for my free electron case. Now, if I say that, okay, I don't want to draw something to infinity, what I can do is that I can fold whatever outside, right? So I have a period, right? Let's say minus pi by a, pi by a. Remember, this is in reciprocal space. I'm talking about Brillouin zone. So let's say this is my period. So I fold. Think of it as you fold it back, right? This line get folded back, mirror image of that. So this line here will become go this way, and this line fold here will become this way. Okay, and so forth. So you can see that you will get this interesting thing. You get this line and then fold to each other like this. Okay, and then you can then leave this out. Okay, you can leave this out. And because if you after you fold it, you have all the information you need. Because if you unfold it, you have the extended zone. So here you have the reduced zone, just showing the first Brillouin zone, which in fact contains all the energy information that you see. So because here outside here, you may be from this part here and this part here, you're talking about the second Brillouin zone and third Brillouin zone. So that's what you do, and so you have and in here you show the parabola is my free energy, right? My free electron case that have parabola, and here I'm showing the energy state of these Brillouin zones. Perhaps all I should do is to show you this one here. So if you have, looking at the free energy case, let me go one. Right, so here we have a free electron case like this. And we said that in a periodic function, this thing is going to split into two. So here we have, look at this zone here. Okay, so originally like this. So you look at this zone here. If each of the period is going to split into two, right, like this. So I have a gap in between this at the boundary point, right, at the boundary point, like this. And then if I fold it back, right, like what I did here, what I got is this reduced. So I have an extended zone scheme. This is a reduced zone scheme, and you got gap in between. Okay, so those are the results of the periodicity of the function that you see. And then people also extend this called a periodic zone scheme. So basically, you take the reduced zone scheme and repeat it on this, because it should not matter how you do it. But most importantly, in terms of logistics, people usually just show the reduced zone scheme, because you can extend it into a band structure like this, right? Or you just show one based on this, focusing on the origin point and see how the extended zone goes. Like this. Okay, so this, what I'm showing here is in fact the periodic zone scheme that I showed you here, and this is the first Brillouin zone. The lighter part, my second Brillouin zone, and these part are my third Brillouin zone, like this. Okay, so I think hopefully I give you a sense of what's going on here. So we've defined the free electron gas model in here. Define a set of k numbers, this wave number, and energy. Right? Once you got k, you get energy. The energy proportional to k squared. you get this parabola in the free energy case. In the case of periodic function, you have the parabola plus gaps, right? So introduce gaps like this. In the case of periodic functions, and you started to modify your K and your energy band like this. But in this case, how do you, so I show you through the physics way, maybe I can show you how the chemists think about it. Perhaps we are more comfortable thinking about this from the LCAO approach, linear combination of atomic orbital approach. And we ask the same question, what does the wave function look like for one of these case states? So let me quickly go to show you this. It's rather similar if you look at this from this perspective. Here you have, again, you take the wave from LCAO, you write it in the same way. You basically take a linear combination, right? So this is molecular orbital, atomic orbital is chi squared, and you have some coefficient in front. So this is, I write it at e to the k n 8 for some, for logistic reason, as we will see later. So think of this as a linear combination of atomic orbital, really. And all you do in MO theory is that you calculate, in quantum mechanics as well, you calculate something called the expectation value for the energy. And the expectation value is defined as two integrals. So don't be frightened by this Dirac notation. So these are just two integral. So integral of this wave function times this operator, which is a function operating like this, right? And divided by the normalization of the electron density itself, if you like. Think of this as the electron density term. Think of this as the operator, energy operator operating on the function, and then you integrate. Okay? So it's really just expectation where you and this is just an operator. An operator is a function, mathematical function, operating on another function, like differential, double differential, right? D squared dx squared. That's an operator. Okay. So if you do that, you take this function, substitute into these guys, right, and solve for these two integrals. Just do the integral, right? And what you end up is that if you take the first integral, what you got is again a double sum structure like this. Double sum structure like this, and you have this integral operating on my atomic function, this chi squared. Okay. So I have this, think of this as a term, no big deal, just a term, some sort of constant. After I do my integral, I will get a constant out. So basically, this is a linear combination of some constant, and this constant depends on my atomic wave functions. And similarly for my density term, my electron density term, it depends on the atomic density, that linear combination of atomic density. Okay? And I assume something called orthogonality. In other words, the two wave functions cannot overlap with each other. So orthogonality means that when something is orthogonal, it means that you cannot overlap one onto the other. And the way mathematically to define it is to say that when these two numbers is the same, this quantum number m and n is the same, that integral should be 1. If they're not the same, they should be 0. It's kind of, it's saying exactly the density. If you have the density of the same function, they should give you something. If you are trying to integrate density of different function, it should give you 0. Okay, that's how you orthogonal means. And so you can then define these things depending on m and n. These integral constant can be alpha and beta, right? Those are just value from this integral, right? And then I can rewrite this term into something simple. I can rewrite it into alpha plus beta, and then